all right? This only happens for Majorana neutrinos. And these lectures are for standard neutrino physics. But as Mateus told you yesterday, some theorists believe that neutrinos are Majorana, and that is my standard model. Neutrinos are Majorana for me, okay? So this is why this is on the standard neutrino lecture. All right, so how does that work? So to calculate that, you need to calculate this amplitude, and this amplitude is not so trivial, not only because there's a lot of stuff going on here, but there is also a nuclear form factor that is not easily calculable. You need to either use non-perturbative methods, phenomenological methods, or some chiral perturbation theory approaches, which are not trivial. But the point is, these couplings here, they're essentially UEI, UEI, and in this propagator, you have the mass of neutrino I. So when you square the propagator, you get something like MI here and a Q squared out, approximately. So this amplitude is proportional to UEI square MI times MI, okay? And we call that some people call MEE, some people call M beta beta, the effective double beta mass, which is the sum in I U E I square MI modulus. Well, sorry. The amplitude does not depend on the modulus. Now, let's check what that is. I wrote here the PMNS matrix, cosine 1, 2, cosine 1, 3, etc., and the Majorana phases. If you multiply this by that, I don't really care about what is down here because I want the UEI, not the mu I, not the tau I. If you multiply that, you see that every single entry has a phase. Oh, the lights, maybe. French. All right. Yeah, it was feeling a bit dark here. So there are phases here, and this is U square, so the phases do matter, okay? So the first thing is that there is a part here in this amplitude, which is the nuclear matrix element, and this is quite uncertain. At the plus or minus about 30%. It's so, you know, there is a big uncertainty there because of nuclear physics. Now, when you calculate the process, as Graciela just told us 5 minutes ago, you get an amplitude and you square the amplitude. When you square the amplitude, there will be some complicated stuff, but this guy here gets squared. So your because you're going to be sensitive to the modulus square of that, what we are going to call the MEE, or M beta beta, is the modulus of this, okay? And I just want to call the modulus of that because I want to plot it. And I don't know how to plot imaginary stuff. I can only plot like real stuff. All right, so the double beta decay rate depends directly on this, okay? So I want you to be aware of a very, very, very common plot that you see in any conference when people present about double beta decay. That is a plot that is sometimes called a lobster plot. And again, I think physicists really like to sound cool and fancy. And this is just a horrible name as usual. So the lobster plot is this. I should take this one. So you take the mass of the lightest neutrino, and you are plotting M beta beta. Oh, sorry. Well, I'll be calling this M beta beta. I always call this M beta beta. I tried to call it MEE, but I just can't. So MEE is equal M beta beta, okay? Beta beta for double beta. So remember, neutrinos can be at the normal mass ordering, where the mass of the neutrinos will be let me call M0, the mass of the lightest guy. The lightest guy would be the first one. Delta M squared, 2, because we do measure that, plus M1 squared, which is M0 squared, square root. M2 squared minus M1 squared plus M1 squared, that's just M2 after the square root. And delta M squared, 3, plus M0 squared. So for the normal ordering, you got this. For the inverted ordering, you would have, let me just put this here. For the invert ordering, you had 1, 2, 3. And then the lightest neutrino is actually M3. So the lightest one would be this guy. And then M1 is delta M squared 3, minus, remember, if you're in inverted ordering, delta M squared 3, is negative, right? It's M3 minus M1, M3 is small. So it's root minus delta M squared 3, plus M0 squared, and then the other one, whatever. So they're slightly different. In terms of number, and I'll give you like this plot very soon. In terms of numbers, I keep telling you that the UEI square is roughly 0.6, 0.4, 0.02, very roughly. So when you have a light mass, another light mass, and a heavier mass in the inverted ordering, but you're multiplying that by large number, and small number. When you do that, you see 2 small times 2 large, 1 large times 1 small, with phases. So this is essentially this problem. You have 3 segments, line segments, UE1 squared M1. Then there is UE2 squared M2 with some angle, for example, one of these phases here, right? Or a combination of phases. I can just call that, well, I don't need to call that anything actually. And then UE3 M3 and another angle. And your M beta beta is this distance here. Okay? Simple as that. It's just you're summing up 3 complex numbers with whatever phases. We never measured these phases, so you don't know what they are. So it's 3 line segments with angles given by the phase. Okay? So when you do that for normal ordering, you get the following. As you start with 0 mass for the lightest neutrino, there is essentially a range for M beta beta that is given by the uncertainties on your mixing angles, but more importantly on the on the phases here. Okay. For example, if this guy has 0 mass, then I have only 2 segments. I can have 1 segment, or I can have 1 segment, another segment, or 1 segment, 1 segment. So I can have my M beta beta to be big, or intermediate, or small. So that gives you a range on the values of M beta beta. This is a log plot, okay? Log. So as I go here, M lightest is very small. Eventually, it gets to a region where these 3 line segments, they can be pretty big. Well, can be as big as possible. Or you can actually form a triangle. and connect the first to the last, which means that m beta beta is 0. So if you can form a triangle, you go down to 0, like identically 0. We can ask if nature is so mean to do that to us that it would give us Majorana neutrinos, which is super interesting, with not so small masses, which is super interesting, but the phases will mess up your experiments. Nature is not like that, but fine. It is a logical possibility, okay? And this guy here, it's the maximum value. And then as you keep going larger and larger mass, eventually you can't cancel things anymore. But more interesting, if you send masses to the mass of the lightest one to infinity, all these masses become degenerate. Okay? And if these masses become degenerate, now you have 3 line segments of some mass times 60, 40, and 2%. You cannot ever close a triangle there. So there is, again, a range. And everything's proportional to your mass of the lightest neutrino, which is kind of the overall mass. So that keeps growing as the mass of the lightest neutrino grows. That's a lobster, apparently. I think it helps because to see a lobster if you draw on red. But so this is how you understand this m beta beta plot, the effective double beta mass, in terms of phases, oscillation parameters, and mass splittings. Okay? That's for normal ordering. Now let's check inverted ordering. Inverted ordering is slightly different. M3 is the lightest one, so M3 is small. But UE3 is small. So your line segments have small times small, that's really small, large times large. So to start with, even if this guy is 0, these two guys here are relatively large multiplied by large mixins. So you cannot cancel things away. And as you grow M lightest, you just don't find any place where you can cancel this, close that triangle with these 3 line segments. So for inverted ordering, you start with some allowed region, and as you vary M lightest, you do this. And eventually, if M lightest is very large, these masses get real close by, and it really doesn't matter who is the lightest or who is the heaviest. So you don't see any difference between, for this process, between normal and inverted ordering. Okay? So this is inverted ordering. I don't know if you have ever seen this plot. Has anybody never seen this plot? Holy shit, nobody has seen this plot. Oh, God. Okay. So, that's called the lobster plot. Okay, that's fine. If you never saw this plot, this is the standard plot that every double beta decay experiment shows when they want to say what they can be sensitive to in these processes, right? So basically, this tells you that double beta decay experiments can put a constraint on this thing, on this M beta beta. This is the physically allowed region for M beta beta, depending on what we already know of oscillation physics, normal ordering and inverted ordering, and the mass of the lightest neutrino that we don't know. And they put a constraint, for example, here. Whatever is above this is ruled out. The way they show these plots sometimes can look a little bit misleading. Instead of doing ruled out, they show a band. They show things like a band here. And this could be, for example, one experiment, Kamland Zen, which is, I don't know if you remember Kamland that I discussed previously. This is essentially the neutrino oscillation experiment, Cumland, but now you put a xenon balloon inside that can give you double beta decay. And then you stop doing neutrino oscillations, and now you're doing double beta decay physics. But it's the same detector. Sometimes they show the band. This can be very confusing because usually a band means that you're ruling out what's in the band or you're allowing what's in the band. This is not what they mean. What they mean is that within the uncertainties of nuclear physics, the constraint can be either down here up to up here. So they rule out everything from here to up, or here to up, or here to up, depending on the nuclear physics matrix element. It's just a bad way of showing the result, in my opinion. But honestly, I actually do not know of a better way, so I shouldn't be complaining that much. So you know, when they show a band, that's not what they have seen. That's just the uncertainty on what they can exclude, right? Think about it. The experiments do not measure in beta-beta. Experiments measure how many decays have happened, and if you didn't see any, they measure a lower limit on a lifetime. This requires way more to be extracted, including the matrix element that has a big uncertainty, right? Now, there's a little bit more to this that I want to say. First, that there is another kind of experiment that can measure the neutrino mass. I mentioned it briefly a few times, the Catherine experiment. So Catherine measures tritium decay. So, well, Catherine has a bunch of tritium. Tritium decays to helium plus E plus nu E. Gases is plus, this needs to be minus, this needs to have a bar, right? So it does that. You don't see that because that thing is on the source. You don't see that because that's a neutrino. So what Catherine does is to measure the electron. It has a very fancy way of measuring the electron, but what they want to do is this. We know the mass of these two things. So the maximum energy of the electron depends on the mass of the neutrino. If the neutrino is massless, this is the energy of the electron, this number of events. The endpoint spectrum of the electron can go like this. If the neutrino is massive, it can go like that. Of course, this is like super duper zoomed in. The endpoint is about 18 keV. And you know that the mass of the electron, the mass of the neutrino is typically below the electron volt scale. So this is like 1 eV in 18,000, okay? This is if neutrinos are massless. Let me call m nu E effective. And this would be for m nu E effective not equal 0. Where m nu E effective, if you think about it, when you decay, told you that this is not a real particle. It's a sum of 3 particles. So you're decaying to nu1, nu2, and nu3 with coefficients E1, da-da-da. So your effective nu E mass for this is UEI MI square, I believe. Yeah. So what that tells you is that Catherine can put a constraint on some combination of masses. Because we know the mass splittings, Catherine can put a constraint on the mass of the lightest neutrino. The current constraint, I think, is about 2 electron volts or so. You should probably check. You should check at some point the slides of this conference. If you check the slides of this conference, you'll see this baby here. You'll see this number here for real, and many other stuff. So, you know, if during the weekend you want to like see why we are teaching you all this, just Check Neutrino 2024. This one, 0.4. Point 4 EV. All right. So that one is more like no. It's not, no. It's in the middle in a linear plot. But I told you that this is a log plot. Yeah, yeah. I remember the result. All right. So good, good, good. So 0.4 EV, and you are touching the inverted ordering region. So you can actually put a bound here, which is scattering. Technically, there are two lines, right? Because normal versus inverted ordering, and this is on the mass of the lightest neutrino. I don't want to draw two lines because I would need to draw even one more line here, and then you would not understand if there are like 7 lines crossing. But that's scattering. And then another thing that you can look at is early, somewhere in the early universe, not super early, neutrinos start streaming away, and if they are if they are massive, they take out more energy, and they change structure formation. For example, they can also change the structure of CMB. So cosmology is sensitive to the sum of neutrino mass. So cosmology gives you a bound on the sum of neutrino mass, of all neutrino masses below. Does anybody remember the result from, is it DESI? 0.1 EV? And this is already touching the what is actually possible for inverted ordering, right? For normal ordering, the mass of the neutrinos, if I assume that one neutrino is massless, the mass spectrum is 0, root of delta m square 2,1, which is 0.008 electron volts, and root of delta m square 3,1, which is 0.05 electron volts. So the sum is about 0.06 electron volts. For inverted ordering, it's essentially the same, but these masses here are essentially this, right? Root of delta m square 3,1, approximately. So that's 0.05, but you have 2 states, so the sum is about 0.1 EV. So cosmology is starting to cut into what is actually physically possible for neutrino masses. Now, one needs to take a step back, because what cosmology measures is how a structure is formed, how much energy has been carried away in a relativistic way or not. And then within the standard model, and within lambda CBDM, this is the sum of neutrino masses. But it doesn't need to be, right? Calling sum of neutrino masses means assuming standard cosmology and the standard model. Just so you know. It is likely that is the sum of neutrino masses, but you gotta know what you're assuming so that you don't get to the confusion that, cosmology is saying that neutrinos do not oscillate or neutrinos do not have a mass, right? There are assumptions there. And again, it's a measurement, right? So it has some leeway to move here and there. But anyhow, cosmology will give you, so this would be excluded. Cosmology would give you like some other line here. A double line, one for normal, one for inverted, but that can just keep one line, which would also be excluded. So why am I telling you that? On one hand, we can have several tests of neutrino masses, if neutrinos are Majorana, on the same plot. Double beta decay, direct mass measurements, and cosmology. On the other hand, think about what happens if we measure something. For example, imagine that we exclude, well, let's take a simple case. Imagine that we just measure an M beta beta, which is like here or here. Standard model doesn't allow for that. So that would be weird. They are straight lines. Sorry, okay, let me repeat the question. So this is M beta beta, this is M lightest. Kemlin-Zan probes only M beta beta. Catherine and cosmology, this should be straight. They probe M lightest. I'm not using this input. I'm not using this input when I'm drawing this. I'm just saying, if it's normal ordering, Catherine puts a constraint on the lightest mass, et cetera, et cetera. So if you measure something here, can anybody think of what would that mean if we measure an M beta beta mass and the lightest mass here? Can anybody give it a shot? Sorry? That's one possibility. There could be more neutrinos such that when you're summing this up, you don't go from 1 to 3. You could be going from 1 to 4. And then there may be one more kick here of a line segment that makes this larger and this larger, right? There could be one more neutrino. What else? You could not be unitary. For example, imagine that there is more neutrinos, but they are very heavy. So you don't really like exchange them in that diagram here because they're very heavy. But they do have some non-negligible mixing. That will change the relation of this stuff. You want to be a little bit more careful because heavy stuff can contribute to beta-beta decay. But in general, if there is no unitarity, there could be either a suppression or an enhancement depending on what caused the non-unitarity on M beta beta. Another possibility, maybe there is supersymmetry, and maybe something that has nothing to do with a neutrino is causing this. That could be a possibility, and so on and so forth. What happens if, and now it starts to get more interesting, oscillation experiments measure normal ordering, so inverted ordering is ruled out from oscillation experiments in the future, let's say. Cosmology detects a neutrino mass, so we must be in this region, but Catherine doesn't see anything. Let's say that Catherine could have gone down, which they won't, but okay, let me make something a bit more realistic. Let's say we measure inverted ordering, and cosmology measures something here. And then the country constraint goes down, or some other future experiment constraint, and does not see anything. What does that mean? Sorry? Somebody got it wrong. Yes, could be. Could always be. But there is actually something that could be more interesting than that. So when we put constraints, there is also an uncertainty on the constraints, yes. I'm assuming that the uncertainty is already folded in when you put the constraint here. So one thing that could happen is actually neutrinos are not Majorana, right? Double beta decay only happens if neutrinos are Majorana. If they're not, you'll never see this on Kemlin-Zan. Boom, we're done. There could also be other contributions that cancel the neutrino rate to double beta decay coming from other physics. And so it goes, right? Imagine that we measure normal ordering. Kemlin measures some double beta rate. Let's say, I'm running out of colors, I think. Let's say Kemlin measures something like here, okay? And Catherine measures something over there, so it's all good. but then cosmology doesn't see anything. They keep pushing the sum of neutrino mass to be 0. What does that mean? What could that mean? Any brave soul? You can go crazy. There is no wrong answer. Maybe neutrinos were not relativistic then, although if some of their masses goes to 0, they should have been. But maybe something happened that neutrinos had a larger mass or were non-relativistic first and then evolved to something else. Non-trivial cosmological history with some BS beyond standard model physics. Maybe there are other particles in the universe doing stuff to cosmology that will invalidate the simple interpretation as simply the sum of neutrino masses. So, point I want to make is we're going to have several measurements here, and their combination will help us test assumptions about cosmology, neutrino masses, the nature of neutrinos, so on and so forth. Okay? So I hope this is somewhat clear. Yes. So, yes. But it's not published yet. I don't think we're going to publish that because it's a complicated model. But the deal is like, if you had some field in the early universe, like a superlight scalar, that sources neutrino masses, and you had, let's say, a population of neutrinos and right-handed neutrinos, and this field couples differently to this and that, a population of right-handed neutrinos may push the field to some VEV, but as the universe cools down, the field can suffer a phase transition. In one VEV, neutrino masses could be 1. After the phase transition, they can be something else. This is the kind of new physics that could change, in general, neutrino masses throughout the history of the universe. But again, that is like hardcore BSM. It requires several moving parts.
Following our suggestion and going crazy, can we have a region where we have some ultralight dark matter field such that the neutrinos have some refractive index there, but then they get out of this and it changes and you change the sum and not that? Or this is too crazy?
It's not obviously wrong. It could, I mean, the usual, so it's very easy to write a model in which a field changes neutrino masses depending on the density of the field where you are, or the density of the field at some early stage in the universe, right? Like in the early universe, things were hotter and denser, whatever, whatever. What is not trivial is to make sure that this is not ruled out by everything else. So all these things, one needs to sit down tight and start calculating constraints. But the overall idea is that if there is physics beyond the standard model, it could change cosmological history, it could affect double beta decay in a non-trivial way, and so on and so forth. So when people put all these constraints here, there are several assumptions of standard model, standard cosmology, standard this, standard that. So let me tell you one more thing about, how many minutes do I still have? Okay, one more thing about double beta decay, and then we can have a quick excursion on non-unitarity. One more thing about double beta decay, and this is a theorem actually. It sounds more important than what it is, but it is kind of cool. It's called the black box theorem. And here it is. There are no stupid questions.
Mass is something that is positive.
Yes.
It's a positive number
Yes.
or 0.
Yes.
It never could be negative.
No.
Okay.
No. So, that is a great question, actually. For example, let's go back to Mateo's talk. I hope he doesn't get mad at me for being in his turf. But remember, the masses of fermions, let's say electrons, they come from this. the Higgs gets a VEV, and this ends up having something like Yukawa, VEV of the Higgs, there is a root 2, it's actually quite important, electron left, electron right. Okay? Imagine that this number is negative. It could be negative, could be imaginary even. I can always rephase my fields. I can just do electron right goes to exponential of I eta electron right. And sorry for E's everywhere. And I can rephase the fields. There's nothing wrong with that. Like quantum mechanics, you can rephase a bunch of stuff. This phase usually doesn't show up anywhere else if it's like a general global phase. And you just phase it out some e to the I whatever from this. Why am I telling you that? Because anything that can be rephased, and a sign is just a rephasing, right? It's just like e to the I pi, it's not physical. So even if the electron mass looks like it's negative, it is unphysical to be negative because I can always rephase things away. For you to have a negative mass, like some people like to talk about tachyons, particles with negative mass that go faster than the light. Usually these people do not have a PhD in physics. Usually it's crackpot, yeah. Unless like you have a real formal framework which allows for that. And there can be one, but usually this stuff has a whole mathematical structure and more or less symmetries that allow you to do that. Within standard model and local QFT and all that, no negative masses. Any more questions before I talk about black box?
Just to mention, I just remember that today I saw in the archive that is a paper that is called The Cosmological Preference for Negative Neutrino Mass. So I suggest to read.
So here's the deal. And this is a big problem of nomenclature. Usually, so I don't know what the paper does because I didn't read it. But usually when people say a preference for negative neutrino mass, what they mean is a preference for this to be negative. If you look at the PDF for the sum of neutrino masses, they go like, this is 0, they go like this. So this is what people call a preference for negative neutrino mass. But again, we need to take a step back. Cosmology does not measure neutrino masses, right? Cosmology measures like structure formation.
Okay.
Cosmology measures the CMB spectrum. And then out of that, you do a standard model, you do standard cosmology, and you extract that the sum of neutrino mass should push things to this direction or to that direction. But the measurement is not sum of neutrino masses,
So
right? So cosmology has a preference to see, I don't know if it's more wiggles or less wiggles on the CMB,
Okay.
suppression, and that, if neutrino mass could have been negative, would have given you a suppression in an equation.
Okay.
But it is not neutrino masses, right? Cosmology does not measure neutrino masses.
Okay, so it's just the sum of the masses, but not, for example, the individual mass that they call that is negative. Not necessarily.
So wait. So here's the thing. When people quote this,
Yeah.
implicitly what they mean is not masses. What they
Okay.
mean is a parameter in an equation.
Okay.
This parameter within standard cosmology is the sum of neutrino masses.
Okay.
But, for example, imagine that I measure this.
Okay.
I am not measuring neutrino masses, right? I'm measuring an electron spectrum. That's what I'm measuring. It turns out that this difference within standard model is related to neutrino masses in a very specific way. But imagine that I found something here, or imagine that I found something over there. That doesn't mean that neutrino masses are negative or like are 10 electron volt. It means that there's something fishy here which my theory may not be able to explain.
Okay.
So this, from cosmology, is a parameter in an equation that can be mapped to neutrino masses within a framework, right? But it doesn't mean that cosmology wants neutrinos to like travel faster than light or anything.
Okay.
That is not a correct interpretation.
Okay, okay.
Is
Thank
that a true statement? Are you happy
you.
with? Okay, good. You're also happy? All right, I got two people who understand this business happy with me, so good. All right, so no negative masses. What I was talking about? Black box. So black box theorem. Here's a funny fact. How can you tell that neutrinos are Majorana? For example, imagine that I measure this. I measure double beta decay. Can I tell that neutrinos are Majorana necessarily? That is actually a not trivial question. What I can tell from this is that if I measure double beta decay, I'm measuring the violation of lepton number by 2 units. But are neutrinos Majorana particle or not? Here's the deal. There is a little theorem, which requires some imagination, but it is still a theorem, that if you measure that, no matter what causes that, neutrinos do have a contribution to their mass, which is of Majorana nature. Maybe it's dominant, maybe it's not. But it needs to have a non-zero contribution of Majorana nature. And it goes like this. If this thing is happening, but let me write like this. If you have 2 neutrons, there's a black box here, so black box theorem. I'm going to 2 protons, and I'll put arrows so I can keep track of the arrows. And 2 electrons. Here's what I can do with this operator. And you should brace yourselves for a second. Here's my black box. Arrows coming out, electron, electron. Coming out, proton. I don't remember who comes. I think this one comes out. This one comes in, so proton, neutron. Come out, come in, proton, neutron. So I just twisted this and rearranged the lines. Not a big deal. But what I can do now is I attach a W here. Now this neutron becomes a proton. And I close one loop here and one loop there. This is physically possible. I attach a W here. So this guy now is a proton. And when I attach a W here, I get a neutrino and a neutrino. So this is a Majorana contribution to neutrino masses. It is a horrible thing. It looked like Mickey Mouse, I guess. It's 1, 2, 3, 4 loops. So the relation between that non-zero contribution, Majorana mass contribution to neutrino masses, to this, given it's a 4-loop diagram, is super like small and far away and indirect, but there is. So if you measure double beta decay, no matter what, there must be some non-zero contribution to neutrino masses, which is Majorana. If you put a real model, usually you don't need to do Mickey Mouse. You don't need to go 4 loops, right? If you put a real model, you might be able to do it either directly, just like seesaw, as Mateus will tell you, or maybe 1 loop, maybe 2 loops. But usually you don't need 4. But the fact that there exists a contribution at 4 loop, given whatever gives you a double beta decay to neutrino masses, which is Majorana, tells you that any violation of lepton number, like that, can be translated to a contribution to neutrino masses. This is an interesting theorem. I'm not entirely sure if it's useful, but it is interesting, right? If you measure that, there is something Majorana about neutrinos. I don't know if I have time. Let's see. I have 10 minutes. Oh, man. What do I want to do in 10 minutes? Maybe I'll tell you a little bit about non-unitarity. Are there questions here? All right. So let me tell you a little bit about unitarity. And let me start with something that we're discussing before the class with some students, and it's a common misunderstanding in neutrino physics. When people talk about the PM&S matrix, they keep going, oh, the PM&S matrix, the mixing matrix, blah, blah, blah. Yeah, it is the mixing matrix. But, for example, imagine that I have 3 neutrinos, standard ones, plus 1 neutrino, okay? What happens to the PM&S matrix? How big does it get? The usual PM&S matrix is 3 by 3. So what do you think it happens to the PM&S matrix if I have 1 extra neutrino? That is the typical misunderstanding. Sorry for setting you up. So what happens, like many people say that PM&S becomes a 4 by 4 matrix. If I add 1 neutrino, 1 sterile neutrino, let's say, to the standard model, how big does the PM&S matrix get? And what you see, even in the literature, is people writing a 4 by 4 PM&S matrix. I don't need it to remain square. And here's why. Let me go back to what is the PM&S matrix. The PM&S matrix is a coupling. The PM&S matrix is defined by, maybe there's a root here, right? I have a neutrino of some flavor alpha, let me put it here. U alpha I of a neutrino I, a neutrino mass eigenstate, gamma mu, P left, lepton alpha, and a W. This is what defines my PM&S matrix, where these guys have a well-defined mass. There are only 3 charged fermions, charged leptons. So alpha can only be E mu tau. My PM&S matrix will never be more than 3 on the charged lepton side, right? So because when we say, oh, you connect this to that, so it's n by n, we are forgetting what defines a flavor of a neutrino. A flavor of the neutrino is defined by weak interactions. And we only have electrons, muons, and taus. There's no other charged lepton. So because of that, the PM&S matrix is 3 by something. You could have 75 neutrinos that do not feel weak interactions. So I here could go from 1 to 78. But we only have 3 charged leptons. So the PM&S matrix is either 3 by 3 or rectangular, right? What, 3 by n? Yeah, 3 by n. What many people do is that they just complete the square because people love square matrices, right? I mean, it's reasonable to work with square matrix. I also do that. But just keep in mind that physics, if you complete the square, let's say that you draw a 4 by 4 matrix here, physics cannot depend on this last line. This last line is unphysical. It's just because I like to work with square matrices, okay? And that means that it's unphysical because there is no 4th lepton. Now, what does that have to do with unitarity? Do I still have 5 minutes? 4? Okay. What does that have to do with unitarity? Well, imagine that in my neutrino masses, like what Mateus told you the other day, I have several extra neutrino states. And now my neutrino can go from 1 to nu I can go from I1 to, say, 6. I have 3 active neutrinos and 3 sterile neutrinos. My PM&S matrix is going to be something like, there's a 3 by 3 guy here, and I'll just separate logically from something else. This whole thing here, when I do U dagger U, I should get a 1. Is that U dagger U or U dagger? U dagger, I guess. I should get a 3 by 3 identity, right? Because when I sum up this, the square of that, I should get 1. Sum up the square, I get 1. Sum up the square, I get 1. But what I observe experimentally may not follow that. So imagine that I produce a mu neutrino, which is supposed to be this. And let's just say I goes from 1 to, for example, 6. But imagine that I try to produce a mu neutrino from pion decay. So a pion decay decays to mu and a neutrino. But imagine that these extra 3 guys here are actually heavy, say 100 GeV, each of them, right? Pions cannot decay to a 100 GeV particle. So this guy decays to what is not really a nu mu. It decays to something that tries to be a nu mu, but is not a nu mu. Because it cannot produce the 3 extra states which are heavy. So the, nu mu from pion decay, which is not a real nu mu, it is a part of your PMNS matrix here, which is not unitary because it's not the entire thing, times nu 1, 2, and 3. So because of that, it is interesting to look for the unitarity of this PMNS matrix. Because you could be probing indirectly the existence of new particles. In practice, we actually know neutrino physics well enough that we know that if there is stuff here, the mixing needs to be small, right? There are other ways to probe that. Things like, for example, at the LHC, right? I can hit proton-proton, produce a W. We go back here. I can produce a W boson, let's say off-shell. And the W boson can decay to a lepton, let's say a tau, and a neutrino 4, which is 100 GeV. I mean, it's not real decay, right? Because the W is virtual. So at the LHC, I can do this. Quark, quark, W, neutrino 4, and then, I don't know, whatever lepton you want. Where this neutrino 4 is very, very heavy, say 100 GeV. So this is a different way of probing non-unitarity under a specific assumption of the model. The last thing I want to say in my last 45 seconds on non-unitarity is this, is that there is one extra thing about non-unitarity which is very, very tricky. We have been talking about measuring mixing angles, right? Measuring what? Dune will measure theta 2, 3, diabase, theta 1, 3, and so on and so forth. But again, experiments don't measure mixing angles, right? When you turn on an experiment, there's not like a little theta shining for you. Experiments measure events, and events can be translated into a oscillation probability, which within the assumption of standard trino-trino oscillation and unitarity can be translated into mixing angles. If you drop this assumption, you need to be very careful with what you're measuring. And here is, this will be a great closing for my lectures. Here is what we actually measure. This entry, UE3, is measured by reactor neutrinos. It happens that within the standard framework, UE3 is S13. This entry, U mu3, is measured by accelerator, nu mu to nu mu. The product of these two things is measured also by accelerator, neutrinos, but on the appearance channel. Theta 2, 3, theta 1, 3, I don't know if you remember, but in the appearance channel, appearance goes like sine squared theta 2, 3, sine squared 2, theta 1, 3. And because the product, there is a phase here which doesn't phase out from the whole thing. We also measure a combination of these 3 things here with neutral current measurements in solar neutrino experiments. That's the SNO experiment. And we measure a combination of, I don't have colors anymore, maybe this one, a combination of this with solar experiments. This, you gotta have a tau neutrino beam. That's hard. This, you gotta have a tau neutrino beam at distances like 30 times the dune distance. That's even harder. Here, you gotta measure muon neutrinos at solar distances, like instead of doing 800 kilometers, you would do 24,000 kilometers. 24,000. It's a bit far. So if you think about it, and this is just a sum, right? You don't measure every single thing individually. This is the sum of the squares of this thing. So this, you measure that it sums up to 1, but you don't measure anything from individually. So we have a 3 by 3 matrix, and we have measurements of essentially 1, 2, 3, 4 independent quantities, plus a little bit here. The PMNS matrix is parameterized by 3 mixing angles and 1 phase, 4 quantities. So we are barely measuring what we need to measure. If you want to test the unitarity of the PMNS matrix, now you gotta give me something else. You gotta give me a measurement that can over-constrain this matrix here. And that's why it's so hard to do non-unitarity in neutrino physics. So I think with that, I should be done, right? Thanks for attending the lectures.
Thanks, Pedro. I think we can jump to the general questions, right? And then you can come up with questions to Pedro naturally, and also to Graciela.
All right, questions, comments, complaints.
Are you satisfied with this unitarity discussion?
Na hora que eles estavam montando os experimentos, por exemplo, quando tem a relação L sobre E, que você não tinha informação da term square, como que eles determinaram esses padrões? Eles tinham uma noção de valores?
That's a good question. So the question is about when people are designing experiments, if they need to optimize for some L over E, but you don't know delta M square, what do you do? And it's not a trivial answer. There is a lot of stuff that went in the way. For example, there were experiments at Los Alamos. There is one specifically called LSND, which sees has an energy, a neutrino energy of about 30 MeV, and a baseline of about 30 meters. And if you see this L over E correspond to a delta M square of roughly 1 eV square. So they did the experiment, and they actually found an anomaly, which until today nobody really understands, but it's a bit tricky. But like there were experiments that they tried to measure stuff, and it was just not ideal, right? But you also got to remember that neutrino oscillations was not discovered like super duper willingly. For example, Kamiokande in the time, it was not constructed to measure neutrinos. It was an experiment constructed to build to measure proton decay. And then their background was weird, which is atmospheric neutrinos. And the weird background actually gave them a Nobel Prize, so experimentalists can be very lucky, you know. They shoot in a direction, they hit something else, and they still get a Nobel Prize. But that was great, right? When you measure atmospheric neutrinos, you have one mass splitting. One is done. There's one to go. The one to go is actually hard. When they detected solar neutrinos, the story that I told you about the resonance, matter effects being small for low energy and large for high energy, etc., that works because I know the mass splittings. At the time, there were several regions which could have been explained, several regions in delta M square mixed angle, which could explain the solar neutrino paradigm, the solar neutrino puzzle. Fleshing out these regions was not trivial. There was one experiment, which I think this is right, there was one experiment which was key to flesh out this region, which was Kamlan. But you could have imagined that Kamlan could have found something else. If I remember correctly, Kamlan was built to rule out what they call the large mixing angle solution of the solar neutrino problem. And they ended up discovering it. But it is a great question. For example, the Minus experiment. The Minus experiment at Fermilab was built when the mass splitting from the Japanese experiment there was a good fit at about 3.5, I believe, or 4, 10 to the minus 3 EV square. And if you remember, the real value is actually 2.5, 10 to the minus 3 EV square. Maybe it was 5 or so, I don't remember, but it was larger, which means that they built the experiment in the wrong baseline. They actually managed to change the configuration of the magnetic horns to change the energy of the neutrinos, the flux, and get an experiment that's a little bit closer to the oscillation minima. But if you look at Minus, the neutrino spectra is like this, and the oscillation curve for their baseline is actually like this. So the peak of their spectra is not at the minimum of the oscillation curve. And that is not because they wanted, that's because this was the best information they had at the time. So it's not trivial. It's not trivial.
Professor, ali nesse plot tem um limite de exclusão do Kamlan vindo de cima, né? Tem algum prazo, alguma data para que ele exclua, por exemplo, inverted ordering?
So the question is, there is this constraint here. When is this constraint going to come down and exclude inverted ordering? I don't think they can exclude inverted ordering entirely, given the uncertainties on nuclear physics. I think if they are lucky, if the nuclear matrix element is more to the larger side, then they might be able actually to go down here and exclude inverted. But if they are unlucky and our calculations of the matrix element actually overestimated, so the matrix element is a little bit smaller or whatnot, then they might, their end result might actually just cut through normal inverted ordering. Future experiments, I think there is, there are so many double beta decay experiments. I think maybe it's next, might be able to probe the entire inverted ordering. But nobody can, as far as I know, there's no experiment proposed that can go down to this level of the normal ordering. I mean, normal ordering cancels to 0, at least possibly, so you can never reach that. But going down here, it's super, super difficult, right?
So for neutrino-less double beta decay, we know that there weren't any any neutrinos when we look to the electron spectra, right? It can happen because the neutrino is a Majorana, but we can have some dark matter there to make the neutrino.
You mean in the double beta decay?
Yes.
So there are other ways of doing double beta decay. For example, there is a model in which, a fairly simple model, in which the Majorana mass of the right-handed neutrinos that would be responsible to neutrino masses actually come from something like a Higgs, like an extra Higgs. And when you break a symmetry spontaneously, you always get a Goldstone boson, so that's a massless particle. And if you don't gauge the symmetry, the Goldstone boson is there. Like for the standard model, when you break SU2 cross U1, you get 3 Goldstone bosons, and these guys are eaten up by the W and the Z to get their masses. But this is because SU2 is gauged. If it was not gauged, we would have 3 massless scalars or pseudoscalars in the spectrum. But the point is, there are models called Majoron models, where the mass of the stellar neutrino comes from a scalar that spontaneously gets its VEV, but there's no symmetry, gauged symmetry there. So there is a massless particle called the Majoron. I guess Majoron. And the double beta decay would actually be slightly different. It would go like this. At least it could go like this. It's proton, electron, electron, proton, neutron, so that's the same. But then you have the emission of, I don't know why they call a Majorana J, a Majoron J, but everybody calls a Majoron J. Oh, J from Jose? Okay, makes sense actually. You gave the name Majoron? Nice. Oh, I see. Nice. So let me know if I say anything wrong. I'll use the original. Nice. Right. So you have a global U1 lepton number. There's a scalar. It gets a VEV. There is a massless pseudoscalar in the game, which is the Majoron. And then now your double beta decay is not, it still like looks like a double beta decay, but it has more stuff, right? So the way you look for the normal double beta decay, you need to be aware of this possibility to look for this. Because what you see is like the energy spectrum of these electrons, but if there is energy going to something else, you better account for that if you want to like discover something, right? So like people do look for this kind of stuff. And this is like one of the many ways one can do that. It's a very minimal way, I would say, because it's fairly like, there is one particle besides neutrino masses. So, and it's quite motivated. But you could imagine that there are other ways of doing that. So in principle, there are many variations of double beta decay, and they are not all the same experimentally speaking, neither theoretically speaking. So you got to know these things to know what you should be looking for.
Okay, thank you.
Hopefully you're happy with my answer, because I don't want you to be unhappy when I describe your model. Huh.
This was my thesis.
Nice.
I started working on neutrino physics. I started working on neutrino mass models, and I had no idea that neutrinos were so important in astrophysics and cosmology. And because of that, I started working in astrophysics and cosmology. And only later I moved to dark matter. It was the 1980s, and it was starting this. The astroparticle physics was becoming something. And then I am also co-author of the first paper on direct dark matter detection with a bunch of people, Allen et al. So in this case, you're happy to be in a good place at a good time and things like that. It always happens like this. But this was my thesis. One of the 3 papers in my thesis was this.
Nice.
No questions? We still have time. 12 minutes. You look tired. Taking. Okay. So if not, I think we can stop here. But you speakers are there. You can ask your question.
So let me just make a few announcements before we go to refreshments.